Section 2. How do Earth's orbital variations affect global climate? Digging deeper. Earth's orbit and the climate. Earth's axial tilt and the seasons. In the Investigate, you used models and carried out an investigation to explore the different factors that cause Earth's seasons and influence climate. This digging deeper will supply you with more details about each of these factors. Earth's axis of rotation is tilted at about 23.5 degrees away from a line that is perpendicular to the plane of Earth's orbit around the Sun. This tilt results in the seasons on Earth. During the Northern Hemisphere summer, the North Pole is tilted towards the Sun. The Sun's rays are at a high angle overhead. That is when the days are warmest. Also, there are more hours of daylight than hours of darkness. On the summer solstice, on or about June 21st, the Northern Hemisphere experiences the most hours of daylight and the least hours of darkness of the year. During the Northern Hemisphere winter, Earth is on the other side of its orbit. Then, the North Pole is tilted away from the Sun. The rays from the Sun reach Earth at a lower angle. Temperatures are lower. The hours of daylight are less than the hours of darkness. On the winter solstice, on or about December 22nd, the Northern Hemisphere experiences the least hours of daylight and the most hours of darkness of the year. Earth's tilt, the tropics, and the polar regions. The Tropic of Cancer is the circle marking the latitude 23.5 degrees north. The Sun is directly overhead along this line at the beginning of summer in the Northern Hemisphere. The Tropic of Capricorn is the circle marking the latitude 23.5 degrees south. Here, the Sun is directly overhead at the beginning of winter in the Northern Hemisphere. The equator is the circle where the Sun is directly overhead at noon on the equinoxes. The Arctic and Antarctic circles are located at 66.5 degrees north and south latitude respectively. Note that 66.5 plus 23.5 equals 90. The polar circles define the region of twilight when winter begins in each hemisphere. This means that on December 21, when the Sun is directly over the Tropic of Capricorn at noon, it will not be visible from the Arctic Circle. So above the Arctic Circle, there is a period during the winter when the Sun remains below the horizon. The same effect occurs in the Antarctic Circle during the Southern Hemisphere's winter. On June 21, when the Sun is directly over the Tropic of Cancer at noon, it is no longer visible from below the Antarctic Circle. How do Earth's orbital variations affect climate? In Section 1, you saw that paleoclimatologists have developed a good picture of Earth's climate history. The advances and retreats of the continental ice sheets are well documented. Nevertheless, questions remain. Why does Earth's climate sometimes become cold enough for ice sheets to advance? Why does the climate later warm up and cause ice sheets to retreat? The answers to these questions are not yet entirely clear. Most climatologists believe that variations in the geometry of Earth's orbit around the Sun are the major cause of the large variations in climate. These variations have caused the advance and retreat of ice sheets in the past couple of million years. If Earth and the Sun were the only bodies in the solar system, the geometry of Earth's orbit around the Sun and the tilt of the Earth's axis would stay exactly the same through time. But there are 7 other planets in the solar system. Each of those planets exerts forces on Earth and the Sun. Those forces cause Earth's orbit to vary with time. The moon also plays a role. The changes are slight but very important. There are three kinds of changes: eccentricity, obliquity, and precession. These three things are called Earth's orbital parameters. Eccentricity. Earth's orbit around the sun is an ellipse. The deviation of an ellipse from being circular is called its eccentricity. A circle is an ellipse with zero eccentricity. An ellipse can become more and more elongated with a larger major axis and smaller minor axis. When this happens, its eccentricity increases. Earth's orbit has only a slight eccentricity. The eccentricity of Earth's orbit is very small. However, the distance from Earth to the Sun varies by about 3.3% throughout the year. The difference in insolation is even greater. The word insolation has nothing to do with insulation. Insolation is the rate at which the sun's energy reaches Earth per unit area directly facing the sun. The larger seasonal variation in insolation is because of what is called the inverse square law. What you found in Part E of the Investigate demonstrates this. The area of the image on the wall was 4 times the area of the hole. This was true even though the distance from the bulb to the wall was only twice the distance from the bulb to the hole. Because of the inverse square law, the insolation received by Earth when it is farthest away from the sun varies by almost 6% compared to when it is closest to the sun. Other planets in the Earth-Sun system pull on the Earth. As a result, the eccentricity of Earth's orbit changes with time. The largest part of this change has a period of about 100,000 years. That means that one full cycle of increase and then decrease in eccentricity takes 100,000 years. During that time, the difference in insolation between the date of the shortest and farthest distance to the sun has a wide range of values. It can be almost 2%, which is less than now. It can be almost 20%. This is much greater than now. The 2 points that you use to make ellipses in Part D of the Investigate are called the foci of the ellipse. The singular of foci is focus. The sun is located at one of the foci of Earth's elliptical orbit. Earth is closest to the sun when it is on the side of that focus, and it is farthest from the sun when it is on the opposite side of the orbit. Nowadays, Earth is closest to the sun on or about January 5, called perihelion. It is farthest from the sun on or about July 5, called aphelion. That tends to make winters less cold and summers less hot in the northern hemisphere. Obliquity. The tilt of the Earth's axis relative to the plane of Earth's orbit is called the obliquity. The axis is oblique to the plane rather than perpendicular to it. In the Investigate, you discovered that a change in the obliquity would cause a change in the nature of the seasons. For example, a smaller obliquity would mean warmer winters and cooler summers in the northern hemisphere. This might result in more moisture in the winter air. More moisture would mean more snow. In cooler summers, less of the snow would melt. You can see how this might lead to the buildup of glaciers. Again, due to the pull of other planets on the Earth-Sun system, Earth's obliquity changes with time. This occurs over a period of about 41,000 years. The maximum angle of tilt is about 24.5 degrees. The minimum is about 22 degrees. At times of maximum tilt, seasonal differences in temperature are slightly greater. At times of minimal tilt, they are slightly less. Precession. Have you ever noticed how the axis of a spinning top sometimes wobbles slowly as it is spinning? It happens when the axis of the top is not straight up and down, so that gravity exerts a sideways force on the top. The same thing happens with Earth. The gravitational pull of the Sun, Moon, and other planets causes a slow wobbling of Earth's axis. This is called Earth's axial precession. It has a period of about 26,000 years. That is the time it takes Earth's axis to make one complete revolution of its wobble. There is another important kind of precession related to Earth. It is the precession of Earth's orbit. This is called orbital precession. Earth moves around the Sun in its elliptical orbit. At the same time, the major axis of Earth's orbital ellipse is rotating about the Sun. In other words, the orbit itself rotates around the Sun. The importance of the two precession cycles for Earth's climate lies in how they interact with the eccentricity of the Earth's orbit. This interaction controls how far Earth is from the Sun during the different seasons. At the present time, the northern hemisphere winter solstice is at almost the same time as perihelion. However, in about 11,000 years, the winter solstice will be at about the same time as aphelion. That will make northern hemisphere winters even colder. It will also make summers even hotter than today. Milankovitch cycles. Milutin Milankovitch was a Serbian scientist. In the early 20th century, he developed a hypothesis about Earth's long-term climate changes. He claimed that changes in the Earth's climate are caused by how insolation varies with time and with latitude. In his work, he used what is known about Earth's orbital parameters. These are eccentricity, obliquity, and precession. He used them to compute the changes in insolation. Later scientists have refined the computations. These insolation cycles are now called Milankovitch cycles. Climatologists now generally agree that Milankovitch cycles are closely related to the glacial, interglacial cycles that Earth has gone through in recent geologic time. Figure 5 in Section 1 shows how temperature has varied over the past 420,000 years. It is based on a long Antarctic ice core. There is a clear 100,000 year periodicity. It almost exactly matches the eccentricity cycle. Temperature changes seem to have been controlled by the 100,000 year eccentricity cycle during some time intervals. During other time intervals, temperature changes seem to have been controlled by the 41,000 year obliquity cycle. Climatologists are trying to figure out how Milankovitch cycles of insolation trigger major changes in climate. The Milankovitch cycles, the driver of climate, are just the beginning of the climate story. Many important climate mechanisms must be taken into account. They involve evaporation, precipitation, snowfall, snowmelt, cloud cover, greenhouse gases, vegetation, and sea level. What makes paleoclimatology difficult and interesting is that these factors interact with one another in many complicated ways to produce climate. Milankovitch cycles and Earth's energy budget. Earth's axial tilt causes one hemisphere to receive more direct sunlight and to have longer days than the other. Figure 6 shows that the total energy received depends on latitude. The highest daily amounts of incoming energy, pale pink, occur at high latitudes in summer. Remember that during summers, one polar region has very long days. Total energy received is greater than at the equator. In winter, close to the poles, no light is received. in the black area. Notice that the southern hemisphere actually receives more energy during December, the southern summer, than the northern hemisphere does in June, the northern summer. This is because Earth's orbit is not a perfect circle. In fact, Earth is slightly closer to the Sun during the southern summer part of its orbit. Milankovitch cycles result in changes in Earth's orbital parameters. They occur in regular and predictable cycles. At the present time, energy received ranges from 0 to about 50 megajoules per square meter per day. However, if Earth's tilt or orbit changes, then the pattern shown in Figure 6 would also change just a little. Although the differences might be small, over tens of thousands of years, changes such as slightly longer winters or slightly cooler summers add up. That can be enough to shift Earth into a glacial phase.